Laplace transform is simply this equation, alright, where you integrate some function, alright, in using e minus st, integrating from 0 to infinity. Alright, this is the very key concept. Laplace transform is simply that e minus st integrating from 0 to infinity on a certain function, then you will get some Laplace transform. Alright, so just a quick view on the equation itself. Alright, this is the one that I just shown you earlier. Alright, and what is exactly fs is that this is some function in terms of Laplace. Laplace is s, alright, this is the meaning of it, is equals to, you can also rewrite this thing as the Laplace transform on the function, a certain function in terms of time. Alright, is equals to, as I said earlier, this whole thing dt is the Laplace transform of certain function. So you're going to transform a certain function using Laplace transform. And often people use e minus st. Why? It's because the element of exponential term is very important. Imagine if you differentiate e2t, you have 2e2t. You differentiate again, you have 4e2t. You differentiate again, you have 8e2t. In terms of how many times you differentiate, and you have a pattern using exponential. So we want to harvest this type of patterns in Laplace transform. Not exactly the case, but at least something of such. Alright, so exponential is a very special term that we can harvest. So therefore, in this case, we're gonna use the function of t is equals to t. Alright, so we're gonna Laplace transform t sometime into a Laplace domain. Alright, a Laplace domain, something that is different, using what we have, integrating something times e minus st dt. Alright, so when we're gonna do that, what we have is like this. Alright, and allow me to rearrange this one. I'll just simply bring this thing to this side. I'll just bring this over the side. Alright, now do you find that this integration is easy or not? No, right? It's definitely not easy because you have one term in front of another similar t term. When you see this type of thing, you straight away know that this is two type of functions in one part product. I think you get what I mean. And therefore, you shouldn't integrate normally. You shouldn't integrate like you think that it is like minus s and that's the answer. No, don't do that. Don't freaking do that. Alright, please don't do that. What you need to do is to use integration by parts. You're gonna use this dude over here, and often this equation, alright, is so messy, and you don't know what the hell the meaning it is, right? So a shortcut method I would highly recommend you to remember is this one. Alright, so how does this shortcut method work? The first thing first, you have two variables a and b, and these variables indicate certain function. So I'll assume that I'll take a is equals to t and b is equals to e minus t. Alright, and one very key concept I want to very highly stress on is that when you pick the a, please pick something that is conclusively differentiable. Meaning that if you differentiate t, you have 1, right? If you differentiate again, you have 0. You have some conclusive numbers, right? Something that is not in terms of t, right? Don't pick something that is always looping around. Like if you differentiate one time, you will have minus 1 over e minus s. You'll have minus s e minus st. If you differentiate again, you have s squared e minus st. If you differentiate forever, e minus st will always be there. Don't pick this type of thing. You'll kill yourself. Alright, pick something that is differentiable conclusively. Alright, pick something that is differentiable conclusively like t. Also, don't play cosine or sine. You're just looping around. You always have cosine t and sine t. You're just looping around. Differentiate one time you get sine, differentiate another you get cosine, and then you just forever and forever. It's not cool. Pick something that is that one. Alright, pick something that is pretty cool. Alright, so if that's the case, if I pick A, I'll just simply write the equation, alright, as A integrate B times the integration of B minus a very large integration. Or maybe I should put some colors. Minus A prime, and then this integration B, and then I'll have something, alright, a big integration. Alright, as you can see, we have only two variables, A and integration of B, and an A prime, meaning you're going to differentiate this term, and then the integration of B. So this is integration by parts. Alright, integration by parts. Alright, so therefore, in order to do this, let me just sub in the numbers and you can see what are the things, right? So A is equals to T. If you integrate B, you would have minus 1 over E minus st, alright, because E minus st, if you differentiate, you'll get this value. I assume that you are a professional in integration, so I'll not go into details on that. Minus the large infinity. If you differentiate t, because A is equals to t, if you differentiate in terms of time, you have 1, right? And therefore this is simply 1. And then I just simply continue with this, E minus st. And there you go, you have just done something that is pretty cool. Alright. If happen that this is like still like something like, let's say you instead, if it's t squared, if you differentiate one time, you have 2t, right? So this will become 2t, right? You're gonna do another integration by parts for this one, so you're gonna have another loop. Alright? So this is something that I want to share with you also, but I'll not go through with it. So we have 1 over here, right, for simplicity's sake. So if I were to rearrange, alright, I'll have minus ts e minus st minus, if I integrate, minus 1 over e minus st. So this 1 times this term, this is simply as that. So if I do that, if I were to integrate, I would have 1 over s squared e minus st. Alright, so minus 1 over s times minus 1 over s e minus st. Everything will become this thing. So I'm just simply differentiating, but be careful of the minus and the plus. Alright, and also to remember that this is minus. Always remember this is minus. And then we have the definite integral from 0 to infinity. Alright, this is from 0 to infinity. And therefore we have it, something conclusive, but yet we haven't finished yet. I have to solve for the definite integral. Alright, so I'm gonna take this thing and just place it over here. Okay, and then this is minus. So I'm gonna sub in when t is equals to infinity and t is equals to 0 over here. If you don't know what I'm doing, I'm just simply solving for the definite integral of this thing. Right? If you don't know what is definite integral, or you don't know anything about solving, you just follow me and you'll know what I mean. Alright? So this is simply solving for indefinite integral. I'm just subbing when t is infinity for all of them, minus away when t is equals to 0 for all of them, and then I'll get some answer. That's definite integral. And therefore if I don't do that, I'll have minus ts e minus infinity s e minus s times infinity. This whole thing will becomes 0, right? Sorry, minus 1 over s squared e minus s infinity. This whole thing will become 0 also, right? So be very careful that this term e minus st is always, if it's e minus infinity, alright, I shouldn't have written that. If it's e minus infinity, alright, is always equals to 0 because it's very big, I mean very small number. Alright, you can just type in e minus 1000 or 10,000, whatever. You'll get very small number of 0 in this case. Alright, this is the similar concept I just want to convey. And therefore now I sub in t is equals to 0 for all these terms. I have 0 of course, so anything times 0, 0 is just 0. And then minus 1 over s square e minus 0 is this whole thing is just 1. E to the power of 0 is just 1. Alright, so I just no need to write e minus 0 anymore, I just write as this one. And there you go, you have 1 over s square. This is minus 1 over x square, you have plus 1 over s square. Alright, and you often come with region of, this is region of convergence of some Laplace transform s that is larger than 0. So what is this thing all about, right? And you often also see these things, region of convergence larger than 0, minus a, and you know, weird stuffs going on. Why are there all these things, and how is it coming from, and where is it coming from? Alright, so I decided to actually also to discuss on this. Is that the first condition of all Laplace, alright, all Laplace, you have to ensure that this thing, it's, alright, maybe not, it's this thing, it's minus always, alright, it's always minus some value, alright, it shouldn't be plus. If it's positive, it is not equal, it's something else, alright, it's not something Laplace related or something different, or something that is higher level. But in our case, just take this as minus always. And how does this link there? I mean link to the region of convergence, because sometimes you may not be given e minus st as easily. You may be given as e minus s plus or minus k, right? In this case I just write minus k t. Alright, if k equals to 0, then it's just simply e minus st, that's all, right? So if it's k is equals to 1, then you have to ensure that s is larger than 1 in this case. So for example, if k is equals to 1, s is like 2, 2 minus 1 is equals to 1. And then so minus 1, at least you are still having minus over here. So for example, if s is 0.5, alright, and then k is 1, and then 0.5 minus 1, you have minus 0.5, and if you have minus 0.5, you have positive 0.5t, and this is not what we want. We don't want this form, we want something negative over here. Alright, so this is the region of convergence we are talking about, and therefore you're going to take note of what k value it is, right? And it shouldn't be negative on this sector, it must not be negative, because you're going to cancel out with this negative and things will not be right, because you want it always to be negative over here. Right, so I repeat again, this must not be negative. Negative times negative, you have positive. We do not want et something like that, we don't want. We want e minus st, alright, we want this one. Okay, please remember that. Okay. Anyway, so how do we have the region of convergence, alright, where it is equals to 0? Because when k is equals to 0, we have e minus st. This is why we can continue on just now what we have just done using e minus st, right? This is why k is equals to 0, and we want it to be larger than 0. Why? It's because if, let's say k is equals to 0, and then I should use different color, at least something bright. So e minus, and then s minus 0 t, right? If s is smaller than 0, meaning it's negative, so e minus 1 minus 0 t, or in other words, e minus 1t. This whole thing will become et, right? Minus times minus 1, you have plus 1. So you don't want this thing, you don't want. This is why s has to be larger than 0 in this case. Alright, has to be larger than 0 in this case. So I hope that this is the thing that I just want to convey for region of convergence. So you need to be very careful of what type of region of convergence they are talking about. So you're gonna remember this thing also. What type of values you're gonna put it in over here. Alright? Because there's some parameters you cannot do and you wouldn't get certain answers. Alright? I hope this kind of clear you up with some basics of Laplace transform. Alright? And I'll see you soon for something else. Bye bye.